Hello everyone, my name is Kevin Strauss. I am happy to present our new paper, Attention-Based Adversarial Appearance Learning for Augmented Pedestrians in Autonomous Driving. I will introduce our paper from the following perspective. In the beginning, I will provide the motivation. For autonomous driving to evolve from the mere research area to the application domain, it is critical to ensure that autonomous systems are able to guarantee high safety requirements. The capabilities of machine learning-based perception components rely heavily on the availability of large-scale datasets of high quality that form a representative sample of the real world. This is hard to ensure for edge cases, as for example in 2019 a pedestrian was killed by a self-driving test car from Uber, as the perception component in the car failed to classify jaywalkers. An appealing approach to overcome the previously described dilemma is the usage of synthetically generated data. However, for real-world applications their usage is strictly limited. Naively training a segmentation model on synthetic data instead of real data results in a devastating prediction accuracy drop when evaluation is done on real data. The root cause for this phenomena can be identified as the domain gap that is present between the synthetic and real domain, which is characterized by different content and appearance distributions between domains. In literature, this discrepancy is more commonly addressed as covariate shift. To tackle the aforementioned problem, many researchers attempt to minimize the gap between synthetic and real domains by means of generative networks. The majority of them rely on adversarial training. The goal of our augmentation and appearance learning approach is to enable the injection of pedestrians to generate previously non-existent or missing scenarios of pedestrian appearances, where the injected pedestrians should successfully mimic the expressiveness of real pedestrians. We use a 3D model placement pipeline to inpaint virtual pedestrians at suitable spots into existing cityscape scenes. In the initial stage of the pipeline, we leverage disparity maps to calculate the depth map for every image. By enriching each pixel with its depth estimation, we can reconstruct a point cloud representation of each scene. Having this depth information at our disposal, we can now compute locations where pedestrians could realistically appear. For this purpose, a spawn map is estimated that locates collision-free spots. For the actual placement, a 3D pedestrian model is rendered and blended with an existing frame capture from the dataset. Augmentation, however, does not consider lighting conditions of the particular dataset scene. To reduce covariate shift, we provide a domain adaptation model based on an adversarial network which allows to learn appearance and make CAD models realistic. On the adversarial game, the generator is encouraged to perform perturbations in the source images to level out the discrepancies between domains with regard to content distribution. In our setup, this has the undesired effect that in-painted pedestrians vanish instead of attaining a realistic look. In our approach, we propose a new GAN model which handles distribution discrepancies by splitting the discriminator into multiple ones. The motivation behind this method is to reduce the decision-making freedom of the discriminator to overcome distribution discrepancy between source and target datasets. Based on our interpretation, we single out the class with the largest difference in apparition frequency, which results in a pedestrian background splitting. Training of such a two-discriminator network forces each split discriminator to get specialized on the appearance features of the given class and succeeds in learning semantic, consistent translation of pedestrians. For every class-specific discriminator, we adopt its patch-GAN architecture. We clip activations that originate from undesired regions of the input image at each level of the discriminator by using multiple downsampled mask layers. This is represented here in an adapted version of the original GAN adversarial objective that includes binary masks MC to account for class-specific objectives. In practical scenarios, the application of the label-based splitting strategy faces various problems. For a label-based splitting strategy, it may not always be straightforward which regions or classes to single out. Above all, semantic labels for both the source and the target datasets need to be available, which is rarely the case in practice. To remedy these limitations, we extend our model such that it is able to find an adequate splitting strategy in the unsupervised setting where no labels are provided. For this purpose, we devise an attention mechanism on top of the multi-discriminator architecture. This way, an attention map is driven to select those areas to translate which maximize the probability that a discriminator makes a mistake. Regions which are characteristic to a domain are therefore most likely to be included in the attention map and to be translated, as they provide otherwise an easy way for the discriminator to distinguish samples. Our leading hypothesis is that classes which exhibit large differences in apparition frequencies between domains do as well have a domain-specific character. This means we can leverage former attention mechanisms to locate areas that do contain class-shifting regions. To confirm our assumption, we create a novel, non-pedestrian dataset, apply our pedestrian augmentation and appearance learning approach, and analyze to which extent the pedestrian distribution of the generated samples resembles representative samples of the real world. We lay our focus on cityscapes, a large-scale dataset of complex urban street scenes recorded in Germany. We create a customized cityscapes dataset that does not contain any pedestrian information. We then augment the resulting dataset to retrieve a collection of samples that only contains virtual pedestrian appearances. If we investigate the involvement of attention regions in one translation direction, we observe that virtual pedestrians reliably get rendered away and crisp-bordered attention regions restricted to pedestrian-specific content can evolve. We create two further training datasets by applying our appearance learning approach onto the augmented pedestrian dataset. One time we employ a pedestrian background splitting strategy, and another time we leverage attention maps in the augmentation domain and pedestrian labels in the real domain. We evaluate our approach on Cityscape's finely annotated validation dataset. To compare the quality of pedestrian instances that are present in the different training datasets, we train a masker CNN model on each of them and consider their instance segmentation results for pedestrian detection in terms of average precision. For the augmented dataset and its translation, the corresponding average precision values exhibit an enormous gap to the original Cityscapes dataset, which indicates that our approach has not been able to mimic the same variability or visual appearance of pedestrians that are present in the real world. To guarantee a fair evaluation of our appearance learning approach, we manipulate the evaluation process in such a way that it better accounts for the pedestrian variability that can be generated by our augmentation method. Because synthetic pedestrians are mostly placed in the foreground, only pedestrians exceeding a certain pixel height are evaluated, and we manually exclude specific scenes which are not present in the augmented samples, if pedestrians are, for example, severely exposed to occlusion or captured in a non-walking pose. Based on these results, we can conclude that our augmentation and appearance learning approach is in fact able to recreate the real distribution that is present in our modified validation sets better. This means our approach can partly recreate certain pedestrian scenarios. Finally, I give a short outline on future works. Currently, our attention-based method still relies on label information in the real pedestrian domain. We therefore propose a novel approach to achieve the learning of content-aligning attention maps for the translation from the synthetic pedestrian to the real pedestrian domain. Based on our elaborated theory, our main idea is to devise a novel intermediate domain that is characterized by having no pedestrian information at all. We expect that the resulting attention maps, which evolve for the translation from the real to the intermediate domain, reliably identify pedestrian-specific regions through crisp bordered regions. Thank you for listening.